clearly talking about quadratic equations here. This is section 2.1, and in quadratic equations, we've learned to deal with graphs of these pretty well when they were in the form that looked more like this: y or f of x equals a times x minus h squared plus k, where we would know, oh, the vertex is at hk, and this thing grows a times the normal rate of a parabola. In other words, when we played parabolic charades, for those of you who don't know parabolic charades, great game. You come into a room, you act like a parabola, and your classmates or teammates try to figure out what the equation of u is. This we would know. We would shift to the right h, we would shift up k, and then our parabola would be steeper by a factor of a. If we have equation in that form versus this form, then it's pretty easy to know the vertex, know how to create a graph. So I need to complete the square on x, and to do that in this, I have to factor this 2 out, even though it is not convenient. So I get f of x, or y, equals 2 times x squared minus 1/2 x. Notice if I distribute the 2 in, I get 2x squared minus x. I leave a blank. I'm going to bring the plus 1 outside. And then to complete the square, this is review, I take the b term, either 1/2 or negative 1/2, it doesn't matter. I take half of that, divide by 2, or half of that, and I square it. So I get 1/4 squared, or 1/16. And I put my plus 1/16 right in here, but be aware that is an invention of my own. That was not a part of this equation. If I was to distribute the 2 and combine terms, I would get a different value than my original function up here. So what I really just did by putting that plus 1/16 in there that didn't exist before is I really just added 2 times 1/16, or I really just added 1/8 to the right side of this equation. So I could come over here on the left and add 1/8 to balance that, or I can subtract 1/8 over here. So basically I gained 1/8 and I lost 1/8. All's fine, but what I ultimately gained by this was this is now a perfect square. This is x minus square root of 1/16, 1/4 squared plus 8/8 minus 1/8, 7/8. Let's take a look. So I have a vertex at positive 1/4 and up 7/8. I call it the MIVOX. Most interesting value of x is 1/4, because that is when we're squaring 0. If I'm not squaring 0, my values are going to keep getting bigger and bigger and bigger. So that would indicate that my vertex should be when x is 1/4. If x is 1/4, this becomes 0 times 2 becomes 0 plus 7/8 gives me my 7/8 y value. So that's tough on this. I'm going to just still count every unit as 1 on my graph. I'm going to go to 1/4, 7/8, approximately right up in there. Okay. Now, we could go ahead and pick 0 and get out 1 and put in 2 and see what we get, and put in 1 and see what we get. But I know that this parabola is growing at twice the rate of a normal parabola. And what I refer to as standard parabolic growth is simple. A normal parabola, when a is 1, goes to the right 1 up 1, goes to the right 2 up 4, right 3 up 9, right 4 up 16, right 10 up 100. So very, very simple to do this. If this is growing twice as tall, usually I go to the right 1 up 1. Now I'm going to go to the right 1 up double that. So right 1 would get me to about right in here, up double that. So instead of up 1, I'm up 2. Left 1 would take me right over in here. Instead of up 1, I'm up double that, up 2. Normally in a parabola, so these are good points right here. Normally in a parabola, I go to the right 2 and up 4, but now I'm double that. Right 2 up 8 would take me all the way up into about here. Left 2 up 8 all the way into about here. So I end up with this guy, which is my graph. I've got my vertex, and now I want x-intercepts, but x-intercepts, I don't have any. So x-intercepts, none. What does that mean? Well, what do we know about every single x-intercept on here? Every single x-intercept has a y equals 0 value. So if I was to set this equation, got a big mess here. Let me clean just a little bit of that up. If I was to set this equation up here equal to 0, and I tried to solve that, maybe by quadratic formula, I would get a negative discriminant. I can't make it equal 0. Um, Other option for that is I could take this equation, as messy as it is, and try to solve that for x. So my first steps might be to go x minus 1/4 squared equals, I'm going to go ahead and subtract 7/8, get negative 7/8, and then I have to divide by 2. Okay. So at that point, my next step takes square root. I would get plus or minus square root of a negative, and like, oh, don't have any zeros in this case. So there we are. Okay, sketch the graph and identify the vertex. Same problem. Let's go ahead and take a look at this one. We're going to have some similarities here. I want to go y, or f of x, equals, have to factor out -4, even if it wasn't convenient. I get minus 6x, leave a blank. I get minus 41 outside. I need half of 6, 3 squared plus 9. I have to balance that. I made this up. I didn't add 9, though. I really added -4 times 9. I really subtracted 36. So here's my balance. Add 36. Y equals -4 times x minus 3 squared minus 5. So what have we learned? We've learned we have a vertex at at positive 3, -5. So positive 3, 1, 2, 3, 4, 5, -5 right down here. I've learned this is not growing at standard parabolic growth. Standard parabolic growth, I'm going to repeat that on here, would be something like if I went over and up. Here's standard parabolic growth. Over 1, up 1, over 2, up 4, over 3, up 9, over 10, up 10 squared, up 100. But I'm growing at -4 times that. So now, instead of over 1, up 1, I'm over 1, down 4, all the way down here. Left 1, down 4. That's about all the room I have. And once again, we see we have no x-intercepts. Let's go through this process of what we would do if we were going to solve this equation, set this equation equal to 0. Give myself a little bit of working room here. So if I was going to set this equation equal to 0 and solve that for x, that's a horrible 0, I would get x minus 3 squared. My first step, I would add 5 across. I would divide by -4. I would take the square root, and hopefully at this point we would notice plus or minus square root of -5/4. Hopefully at this point we would notice that we have no solutions. But if I continue on, I could get x equals add 3 plus or minus square root -5 on square root of 4, 2. And notice how this is looking like kind of a quadratic formula type answer. That's what I would get through quadratic formula if I went through this whole process. But there we see no x-intercepts. But clearly we knew that once we graphed. So it's nice to have our graph confirm our algebra. Okay, write the standard form of a quadratic equation. So I am looking to put this in y, or f, equals a times x minus h squared plus k. I want that form. Well, if they give me my vertex, I've already got this. Y equals something times x minus the x coordinate. So that's x minus negative or x plus 1/4 squared plus the y coordinate plus -1 minus 1. What I don't know is what multiplier is working here for me. So here's what I know. I've got a graph right now where my vertex is at -1/4, -1, right in this area. Okay? And now I just have to make sure that that graph hits this point, 0, -17/16, somewhere right in here. Okay, I might be accentuating that 1/16, but my parabola has to hit that. Well, I can do that algebraically. Believe it or not, I can do it from a graphic perspective as well. I'm going algebra first. I just have to force my parabola to go through that point. So at some time when the y is -17/16, try that again. When the y is -17/16, the x value is going to have to be 0. So I get -17/16 equals, squared up here, excuse me, equals 1/4 squared 1/16 a, or a on 16 minus 1. You could go ahead and add 1 to both sides, get common denominators, smash together, multiply both sides by 16. I might be tempted to multiply both sides by 16 now. And then I get -17 equals a minus 16. Multiply both sides by 16, so we see that a equals add 16 -1. What's comfortable about that? Well, a being -1 means that my parabola is going to open up down, and that's confirmed over on my graph. To get from the blue point vertex through the red point, I have to go down. So now I can go ahead and graph by saying, well, this is normal parabolic, standard parabolic growth, but upside down. So I would go over 1 over to here, down 1 down to here. Left 1 over to here, down 1 down here. Ultimately, my equation I know now is a is -1. Ultimately, my equation is this. But check this out. This is pretty cool. If we understand standard parabolic growth, look what is happening right over here in green. We are going over this far, down that far. That is over just a distance of 1/4, and we're going down a distance of 1/16. Well, I've said standard parabolic growth is over 1 up 1, over 2 up 4, over 3 up 3 times 3, 9, over 4 up 4 times 4, 16, over 10 up 10 times 10, 100. What would over 1/4 do? Over 1/4 would be up 1/4 times 1/4, 1/16. So we see here that we are going over 1/4 down, but down the expected value. So that would indicate down negative the expected value 1. A is -1 just based on looking at the graph and evaluating it that way. Standard parabolic growth is a wonderful tool to use that allows you maybe to avoid some algebra if you are more of a visual person. So pretty cool stuff. All right, and last problem on this video. Use a graphing calculator to graph the quadratic function. Well, I'm not going to do that part with you, but I can make a pretty reasonable sketch of this guy. And then I know that this thing is going through -21. This is sprinters, intermediate runners, distance runners, if you've been following along and seeing those videos. So I know it's going through -21 here. As it goes through, it passes the baton to a very, very steep, positive sloped line. So this line is really, really steep, steeper than I'm showing here if this was a square graph. And then it wants to pass the baton and look like a positive parabola. So this thing's curving, even getting steeper here. And eventually this has to turn back up. So we would get a graph like that. Not exactly sure what our values are here, but most definitely we have a vertex down here, and most definitely we have two x-intercepts. So how do we find those by hand, the x-intercepts? Well, every x-intercept, no matter where we go, y is 0. So we set this equation to 0. And we have some options to solve this. I could complete the square, factor out a 4, even if it's not convenient, and then solve that for 0. But since I don't need to know the vertex, I would be more tempted to use quadratic formula. But maybe this thing factors. I would need two numbers that multiply to be negative 84, add up to be positive 25. I need a positive, I need a negative. Now, if you don't know exactly what I'm doing here in this factoring method, this is available on another video from the Purple Shirted Nerd website. So you can check that out. But 84, my choice is I need a positive and negative. The positive has to be the big number. I could go with 84 and 1, but those add up. 84 and negative 1 add up to be 83, of course. I could go with 42 and 2. Negative 2. I'm getting closer. Does 3 divide 84? 3 goes in there 28 times. Those are our magic numbers, which means if I can find those magic numbers, this thing factors. I need an outside product to either be positive 28x or negative 3x. I get a negative 3 with a factor of 4 times a factor of 21. Oh, well, it's 1 from the 4 and 3 from the 21, but it has to be minus. And now, first term times first term, 1x times 4x equals first term, 4x squared. Last term times last term equals last term, 7 times, or 3 times 7, but it has to be minus 21, so this is plus 7. This product must be minus 21. And we got it. If we set that guy equal to 0, we get x either equals negative 7 or add 3, divide 4, 3/4. So it kind of supports what I was seeing here. I have a 0, excuse me, I have a 0 over here at, let's try that again. I have a 0 over here at 3/4. And I've got one further to the left than that at negative 7, which, based on my graphing technique, at least makes me feel somewhat comfortable. So there you go, quadratics. Hope that's helpful. Stay tuned. Again, if you're having trouble factoring the quadratics, then I do have a video on that. You can search that at my website.